So, hello everybody. Today I'm going to go over the Blue Waters Wide Area Network WAN upgrade project, covering details about what we've accomplished so far with this project and what we have left to complete. So as Bill introduced, I'm Eric Boyer. I'm a network engineer at NCSA, and I've been with NCSA for a little under 2 years now. I work mainly on designing and maintaining HPC and office networks. I've been working on this specific project for a few months now, so I'm pretty excited to share with you the progress that we've made. If you'd like an idea of what it can be like to be a network engineer sometimes, this slide gives a pretty good idea. So I'd like to talk first about a little bit of the project background and goals. So from the beginning, the Blue Waters project had actually initially budgeted and planned for 100 gigabit capable networking equipment to be put in place to improve connectivity from the Blue Waters system itself to the research teams and science teams. And actually, due to rapid advances in technology and the timing of the network upgrade itself, we were actually able to upgrade more equipment for less cost than was initially budgeted. And so with this upgrade project, we kind of had three driving forces that were kind of our goals. So providing capacity. Now here I'm talking basically just raw throughput and good put, big, large pipes for data to go through. We wanted to provide resilience. So having a redundant network architecture is very important to actually mitigate having downtime and things of that nature. As you all know, the network can be pretty much a foundation upon everything that we do these days. And lastly, connectivity. So actually providing a diverse collection of research resources that people can connect to across the country. So let's take a look at the current WAN design. So our current hardware for our WAN is, we have Juniper EX 8200 devices for the core data center switches. And what's a core data center switch? Basically, it's an aggregation point for all of the data center traffic and the also traffic from NCSA. So we also have the Juniper MX960 platform for our exit routers. And basically the exit routers are just our demarcation point between what we consider to be our network from an administrative standpoint and the outside world. So as you can see, we have a bunch of 10 gig connections to various research networks across the country, which in total are currently 80 gigabits of bandwidth. So some of these networks that we connect to are the University of Illinois campus network, also the University of Illinois Inter-Campus Communication Network, which connects the three University of Illinois campuses together. We have a connection to MRIN in Chicago, which is the Metropolitan Research and Education Network. And that's a really good network to be on for international connections, a little bit of connectivity into ESNet and alternate paths into Internet 2. We have a dedicated Internet 2 connection for a lot of our Exceed traffic. That's a big user there. We also have a dedicated CIC OmniPop connection, which is good for the GLCPC partners, you guys, and as well as connectivity to, again, to ESNet and other DOE sites. Now, we also have a backup path into Internet 2 via the University of Illinois Kearney system, which is the Campus Advanced Research Networking Environment. And it's basically a science DMZ. So in this current design, we have, I was told the laser pointer doesn't show up very well, but so we've got 480 gigabits of bandwidth between the core Blue Waters switch and the core data center switch. And then we have 200 gigabits of bandwidth between the core data center switches and the exit routers. Now here's a look at what we want to go to with our new design. As you'll see, there are many more 100 gigabit connections here. And so for the hardware-wise, we have the same platform going forward with the exit routers, the Juniper MX960s. But for the data center core switches, we decided to go with a new platform, the EX9200. So this upgrade will actually increase our total aggregate external bandwidth to 440 gigabits per second from the current 80. Now the networks that we're going to connect to are pretty much the same, but we're just going to get to them in a slightly different fashion. So again, we've got the University of Illinois campus network, ICCN as well, and a dedicated path to Emeren and Internet 2. But then for our CIC Omnipop and our alternate route to I2, we will get that via Kearney. And we also have a potential connection to a dedicated or a national research network, but that's to be determined. So in this design, we'll actually have 400 gigabits of bandwidth between the Blue Waters core switch and so 400 between here and the data center core switches, and 400 between the core switches and the exit routers. So as you can see, with an upgrade of this caliber, there are lots of technical, complex components that we need to address. There's line card / device upgrades throughout the path. We've got security systems that need to be installed to monitor this 100 gigabit traffic, so a new packet distribution system and optical taps. New optical transponders and repeaters need to be put in place. So given the complexity of the upgrade, we actually decided to break it down administratively into 3 phases. And so let's take a look at those. So the first phase is the deployment of the data center core switches and the exit routers. That's the phase that we're currently working on right now. And I'll go into a little more detail on exactly where we're at in the next few slides. So the second phase will be actually getting the security infrastructure that I mentioned in the previous slide into place. And finally, we need to deploy upgrades to the Blue Waters core switch to allow for 100 gigabit connectivity. So here's a picture of some of the new equipment still on its pallets. And as you can see, these devices are actually quite large. When they're fully loaded, they can weigh around 250 to 300 pounds. So that in and of itself provided some interesting challenges from a physical standpoint when you're trying to mount these in a rack. And so the first real step was actually ordering these things. So we ordered everything in December. We started receiving equipment somewhere in February, I believe. And then the next step was actually phasing out all of the old equipment out of production and removing it physically from the rack so that we could get the new equipment into the racks. We actually did that part in phases, and the main reason for that is to leverage the current redundancy of our current network so that we didn't have to experience any downtime. Given that, as you saw in the slides here, there's redundant connections, there's 2 cores and 2 exits. So that allowed us to maintain uptime. So after we physically got a device out of the rack and put a new one in, the installation process also involves supplying the device with power. We actually power these devices with 2 separate DC power feeds from a DC power distribution system that we have on the data center floor. And so those power cables actually had to be custom made for these systems, which is also part of that process. But also, to get these new switches and routers into production, we need to move all of the cabling from the old devices to the new. And so you'll see this picture on the left here. That was actually taken right after we moved one of the new core switches into production. So the top one is the new one, the bottom one's the old switch. And if you jump forward a few weeks, you'll see a picture on the right there. That is actually of both the new core switches and the core routers in place where they're going to be in the racks. In the top, and as you can see, actually both of the new core switches in this picture are in production. So after we got the equipment racked and powered up, we needed to make sure that it would meet our criteria for acceptance. So acceptance testing really, we basically just needed to develop a set of tests, and in this case it was things such as boot up tests, optical power monitoring tests, previous configuration compatibility testing, and routing protocol tests, all these things. But one of the more interesting acceptance tests was actually testing whether or not each platform could send and receive traffic at the rate at which the vendor specified as possible, which in this case is 100 gigabits going both ways. So the picture here actually shows 100 gigabit network testing appliance that we used to perform that test. And it actually had 4 separate 100 gigabit interfaces on this appliance. And so we would basically hook up 2 of each to each device and send traffic down both ways. And so you would have basically 100 gigabit single stream bidirectional traffic on each interface. And as you can see from the little speedometer thing there, it hit about 99.78 gigabits per second, which the only reason it's not 100 exactly is because you have overhead, so with the traffic. So we've been making good progress. But the real question is, what do we have left? So we still need to bring the exit routers into production. At this point, we actually have scheduled to bring one of them into production this week. And so the other part of that is to bring up the 100 gigabit links to our peers. But really, that part is contingent upon the completion of phase 2 because we need to be monitoring that before we can bring it into production. And finally, we'll complete phase 3 down the line as well. We expect to have this entire project done this summer. And that's actually all I have for you today. So are there any questions?
Comments?
Yes, questions, comments, either is fine.
I'm just curious a little bit about the security side of things. Can you go into a little more detail about what you're going to be doing regarding security?
So I don't actually work too much personally with the security side of things, but I do know a little bit about our security organization at NCSA. So we use a passive monitoring system called Bro to monitor traffic. You know, I haven't worked too much with, like I said, I haven't really worked too much with that, so I can't provide too much detail. But good question.
You want to say anything, Tim?
Tim, do you want to say something?
Hi. So I've worked with them a little bit more. So what we do for securing our exit connections right now is we use optical taps that take a passive copy of all of the traffic, and it gets sent over to a series of intrusion detection systems. They monitor all the traffic that comes across and look for sort of bad actors coming into the network. We tie that in with what's called a black hole router. So if they detect someone attacking the network, we can actually use the routing tables of the routers themselves to shut off traffic to people who are trying to attack us. That allows us to have a firewall-like interaction with an attacker that doesn't actually require inline security. And one of the interesting things that we had to do for the 100 gig connectivity is our security team developed some software that when we detect a large data transfer, that we actually will shut off the flow of that data to the security system, because 100 gig data transfer would be too much to actually monitor.
And I'd just like to mention, if anybody has any further questions beyond this, or if you want to talk about some data transportation challenges that you have, please come see me or Tim after the presentation. We'd be glad to have a one-on-one with you to discuss things further.